Hi everyone. I hope everybody is safe and sound, and so are their family and friends. And I should thank Ayan and Sayantan for giving me this opportunity to talk about what me and my collaborators at ICTS and elsewhere have been up to for past few years. So what I will talk about are some recent developments in non-equilibrium quantum field theory. I will kind of, restrict myself to things that I know very well. Obviously, a very comprehensive review is both beyond the time constraints and beyond what I know. So I will stick to these things and hopefully, like what I'm going to say is sufficiently complementary to what you will hear and what you heard yesterday from other speakers in this workshop, and interesting on its own regard. Okay, so let me start. So non-equilibrium field theory, it's a very old subject. In fact, sometimes we forget that the oldest field theory historically is in some sense fluid dynamics, right? Even before people thought about electric field or magnetic field or something, people knew that you should think about fluids as a field. And it's also a non-equilibrium theory. It's a dissipative field theory, classical field theory, about which we have heard a lot about yesterday and so on and so forth. So it is kind of surprising that even though it is a kind of an old subject, the non-equilibrium quantum field theories actually we understand surprisingly very little. I think one can argue on this fact, but one objective way to say this is the relative paucity of textbooks which cover this field, which are titled as non-equilibrium quantum field theory, as opposed to usual quantum field theories, even thermal field theories, and so on, and the relative paucity of courses and so on and so forth. And even when there are, the contents kind of differ a lot. Okay, so let me kind of start off, with some if you open some standard textbook by say Kamenev or something on non-equilibrium field theory. Or some lecture notes, of which there are many good ones. What they think of as the ambit of what non-equilibrium quantum field theory is. So, a textbook exact definition of a non-equilibrium quantum field theory is via what is called as Schwinger Keldysh Path integrals. Okay, something which goes back to Schwinger and Keldysh, and to some extent Feynman and Vernon and various other people. Like in 60s. So this is a path integral which unlike the path integral many of us are familiar with in the usual quantum field theory course, in an introductory quantum field theory course. This path integral describes the evolution of mixed states. So if you want to describe how mixed states evolve, even in a unitary quantum field theory, you need to use this formalism. So roughly speaking, so I'm not going to review this very much, but the rough structure is something like this: that you kind of have two copies of every field. One I will call as a Ket field, phi right, and a bra field, phi left, and you take the action to be the usual action for phi right minus the usual action for phi left. This minus sign is because the bra fields evolve. By an inverse evolution compared to the Ket fields, as one knows. And the point is that, so these two copies are basically because the density matrix is not just a Ket, it's not a pure state. And it has a bra piece and a Ket piece, and you have to evolve, both the bra side and the Ket side. And you kind of introduce fields to evolve both sides. And the point is that, you kind of solve this field theory, you do a path integral over this field theory with some future and past boundary conditions. So in particular, you said phi r equal to phi l in far future. and you kind of take some particular initial condition which kind of describes some general non-equilibrium mixed state. So this guy, this kind of a path integral, what it does in a field theory is that it computes this generating functional that I have written down here, what I call a ZSK. So here JR and JL are sources for some operators that are turned on in these evolutions. And in particular, it is important that the sources that are seen by the bra side are different from the sources that are seen by the Ket side. Because if you set JR equal to JL, you see that this generative function actually becomes trivial because you can bring the U on the other side. And because U is a unitary evolution, U dagger is identity, and if rho is normalized, trace rho is also identity, so the whole path integral just collapses to just identity, right? Okay, so it's important that you evolve the bra side and Ket side with different sources. Okay, so you take this action SFIR minus SFIL, but when you add forces, you add different sources to the right and the left, and then you kind of define this, right? So this is a kind of a even if you don't have an action and so on, you can think of this definition in Z as a non-perturbative definition. Okay, that is, if you know the unitary evolution, you can always define the quantum field theory this object. And this object is a generating function of what I call a singly out of time ordered correlators. That is, their correlators they're not, so they can generate time ordered correlators as the usual Feynman path integral does, but they also generate time ordered correlators with at most one time order violation, which means that as you read your operators, as from left to right, okay. So usually the time ordered correlators are where as you read from left to right, you go to the time keeps on decreasing, right? Okay, so that the thing that is near the Ket it's the pastmost guy. But you can have you're allowed to have one time ordering violation. That is, you are allowed to have one step where in the product where you can kind of go to the future rather than go to the past as you read from left to right. So such kind of operator products and the correlators of such kind of Heisenberg operators can be computed, are all incorporated in the generative function. So now, of course, already, this is kind of incomplete because you can a natural question to ask is what about, correlation functions where you allow more time ordering violations than one, okay? So it's actually incomplete, which is not often acknowledged in conventional textbooks. It's also something that one of the recent developments, which kind of even goes into the fundamental definition of fundamental textbook definition of what a non-equilibrium quantum field theory is, which is to enlarge it to include more time ordering violations. So I'll come to it in a moment, but let's just go with this textbook definition. The conventional definition you will see in almost all textbooks and lecture notes. And another question is that is this actually a practical object? Is this so this is a kind of a very fundamental non-perturbative definition. It doesn't rely on perturbation theory. It doesn't rely on thermality. It doesn't rely on equilibrium. It doesn't rely on there being a pure state. It could be a mixed state. So it's a pretty general idea, okay? But what do we do with it? Okay, so what do we do with it in practice? So if you are in this business for a while in the non-equilibrium quantum field theories, you soon learn that this is all fine. There's a good definition, but one rarely uses this definition exactly. Okay, I mean, one easy way to see it is just the talks, for example, in this workshop or in any other workshop. That rarely does one directly deal with Schwinger Keldysh path integrals as an object. Okay, and often what you see rather is that one kind of replaces it by various approximations. Often, if you're dealing with the perturbative quantum field theory, in some appropriate regimes, you can make some approximation with kinetic theory. You heard about effective kinetic theory going back to Arnold, Moore, and Yaffe for QCD, for example. In a perturbative regime, various kind of classical statistical approximations. and one works with them instead. Okay, so that's what, so you start with the Schwinger Keldysh path integral, but eventually, so you start with some 1960s, but you soon kind of go back to like Boltzmann and 1860s, if you wish, very, very soon, and go back to kinetic theory, one way or another, with some corrections, of course, but effectively go there and work there. Okay, and most of the discussions, one sees in the literature, even within this kind of theory, is about linear response, about 2-point correlations, about 2-point spectral functions, and so on and so forth. Okay, so that's where I think really we know things very well. Okay, and anything beyond this very limited domain, I think we don't know very much. That's what I meant by saying that our understanding in this field is pretty rudimentary. For example, in equilibrium quantum field theory, we know how to take into account non-perturbative effects. So analytically, you can talk about instantons and so on and so forth in QCD. Numerically, we understand a lot of non-perturbative stuff in lattice QCD and so on. Okay, but as far as this real-time non-equilibrium stuff goes, we really don't have the corresponding things. So most of the time, you just use Euclidean understandings and try to analytically continue and see what can you say about real-time stuff whenever it comes to non-perturbative things. Another thing which is very different from, on quantum field theories, if you're a string theorist, is that we know a lot of dualities, in the sense that, a lot of times string theorists, condensed matter theorists in general, we kind of, know that a particular field theory can become strongly coupled, but often it can be recast into some other effective field theory. In QCD, for example, chiral perturbation theory, and so on and so forth. Okay, and there, you can make progress. Okay, so you can have either an exact duality or a low energy duality, which is basically effective field theory. Okay, and such things are actually not very well known. Non-perturbative, non-equilibrium dualities, where things become strongly coupled. What do you really do? So these things are not really very well known. Okay, in fact, almost the only example of a non-equilibrium duality where non-equilibrium calculations are possible is in ADS EFT, which is an example where the non-equilibrium physics of certain gauge theories, often supersymmetric gauge theories, but not necessarily, are related to non-equilibrium questions in gravity. But as I will soon say, this is fine, but this also has various limitations. Even in ADS CFT, actually we don't understand non-equilibrium things very well. Okay, even in gravity. So this is what I wanted to say. That even in ADS CFT, so you might say, okay, well, so can we actually use ADS CFT to calculate Schwinger Keldysh path integrals? Okay. But soon you realize that nobody actually knows how to compute general Schwinger Keldysh path integrals, the path integral that I defined a few slides ago, even in ADS CFT. Okay, so most of the time one kind of does again some approximations in ADS CFT also, which are like mean field, some large and mean field kind of approximations. Which allow you to not do Schwinger Keldysh again, like what we do in perturbation theory, kinetic theory. We do something like that on the ADS CFT side also, and that's why on the ADS CFT side also we are kind of very limited on how much we can do, in non-equilibrium field theories. So one physical question, for example, which we don't understand how to deal with in non-equilibrium gravity at this point, is about Hawking radiation, especially when the Hawking radiation is interacting. So since, Hawking in 60s, 70s, we know that, black holes radiate like black body radiation, like a black body. And they, so if you just take a free field and put it on a black hole background, you get a black body radiation of the corresponding field. But you can ask what happens if that field is interacting, some realistic Hawking radiation, like what happens if you actually have a standard model in the background of a realistic black hole, okay, which has interactions, electrodynamic interactions, strong interactions, weak interactions, electroweak interactions, various things, right? Like gravitational interactions. So what happens, like if you actually take interactions into account, actually, like there is almost nothing that we know about it, really, like if you really look at it. So most of the discussion about Hawking radiation and black hole evaporation, if you really dig into it, you'll see that, like basically rely on almost free theory calculations, very little interacting theory calculations, okay? And despite the fact that, many things that string theorists are interested in, like, like information paradox, or how does a black hole evaporate, like these related questions, all these questions are reliant on interaction and back reaction, right? Like Hawking radiation comes out and then, the black hole kind of shrinks. How do you model it unless you take into account back reaction and interaction and gravity and so on and so forth? So the point is that, like we do not know, okay, really we do not actually know how to do this in gravity also, okay? And so, like, so our tools are kind of very limited. So this sounds like a very pessimistic overview of the state of things. But I think that, like an optimistic take on this is that there are many things and many challenges, like that we have to face when we think about non-equilibrium quantum field theory and when we try to understand non-equilibrium quantum field theory. Okay. So what I want to describe today is some modest progress towards this, like addressing these challenges. I'll organize my talk into basically 3 themes, like one is about out of time ordered correlations, like something that I mentioned before, about, like open effective field theories, like which I will define in a few slides. And also how to do holography along with Schwinger Keldysh, how to do Schwinger Keldysh in gravity. Okay, what we have learned, and what are things that are yet to do. So a lot of this talk is about, like some new perspective which have emerged over the last few years, and a lot of puzzles those perspectives create. So I rarely have very complete answers. I only have a lot of preliminary calculations, which kind of are very, very fascinating and puzzling and so on. Okay, so so I'll just start with out of time correlations. But are there any questions, comments before I start? Till here, I mean, so this is just a broad, like canvas of how I see the state of things. Okay, so let me start with the first theme, which is about out of time ordered correlations. So as I mentioned, the textbook definition of non-equilibrium quantum field theory is incomplete, and the Schwinger Keldysh path integral actually does not answer every question that one can ask of a quantum field theory, every non-equilibrium question one can ask of a quantum field theory. For example, like you can define a kind of a generalization of the Schwinger Keldysh path integral, the path integral that I defined here, the Z as K, into something like this, where, like you, rather than having one U and one U dagger, you have, like 2 U's and 2 U daggers alternating with each other. So you have a U dagger, U dagger, okay, and the row, right? Okay, so what this object does, like if you kind of think about it for a moment, is that it calculates correlator with a maximum of 2 time ordering violations. Now, the generalization is easy. You can kind of, like string together 2K alternating evolution and inverse evolution operators and define a Z as KK. And this generates correlators with a maximum of K time ordering violations, okay? So what you have is the sequence of generating functions, okay? So a non-equilibrium quantum field theory should not be thought of as a single Schwinger Keldysh path integral, but a sequence of path integrals, okay? With more and more sources, with the 2K number of sources, as K goes to 1, 2, 3, 4, and until infinity, okay? And the sequence of path integrals and the sequence of correlation functions with more and more time ordering violations allowed, okay? So that's kind of, like how, like what we have realized over the last decade, that, like the full set of non-equilibrium quantities and correlations should really be captured by not the single Schwinger Keldysh path integral, but the generalization, which is a sequence of more and more generalized Schwinger Keldysh path integrals with more and more evolution and inverse evolution operators, and more time ordering violations. So these are what I call as out of time ordered correlations, or OTOCs. Okay. So there is a note that there is a very natural and exact hierarchy between these this sequence of generating functions, which are defined this way. For example, like if you take ZSKK with some 2k number of U and U, like KUs and KU daggers alternating with each other, okay, then you just take some 2 adjacent U and U dagger and set the sources equal. Then, like the argument that I gave for the Schwinger Keldysh, like what happens is that those U and U dagger collapse, okay, and give an identity. And what you get is a ZSK K minus 1. That is, you get something with K minus 1 U's and K minus 1 U daggers. So which means that, if you compute, if somehow you give me the path integral, which is ZSKK, I can easily get from that by setting some adjacent sources equal, the path integral for K minus 1. So all information in ZSKK minus 1 is inside ZSKK. So there's some kind of a Russian doll kind of a structure where, ZSK1 is kind of, has less information, is a subset of ZSK2, is a subset of ZSK3, is a subset of ZSK4, and so on and so forth, until you get some ZSK infinity, which kind of contains all the correlations with arbitrary number of time ordering violations. Okay, so you have a sequence of descriptions. Okay, sequence of path integrals which incorporate more and more fine non-equilibrium correlations as we increase K. Now note that, if you have just, let's say, n operators, let's say you're considering such n-point functions, okay, it is kind of easy to convince yourself that the maximum number of time ordering violations is when you kind of zigzag these correlators, right? You take one operator, another operator in the future, another operator in the past, another operator in the future, another operator in the past, another operator in the future, if you think of this as the time, right? Okay, so you can kind of zigzag things, sometimes we call this tremolo, kind of correlators, or some zigzag kind of correlators. And you can easily count that, the maximum number of time ordering violation you can get that way is n plus 1 by 2 if it is not an integer part of n plus 1 by 2. So you cannot get more than n plus 1 by 2 time ordering violations. So which means these finer and finer out of time ordered violations need also a very higher point function. So you need like a large number of time ordering violations, more and more finer correlations are captured by more and more time ordering violations in the correlation functions. And to have more and more time ordering violations, you need more and more operators. So really you're talking about a large, a higher and higher point functions, okay? So the point here is that, so one has the sequence of these things, okay? So there's this exact hierarchy, okay, of correlation functions where, you have of involving higher and higher point functions with more and more time ordering violations, okay? So this whole argument itself is very elementary, right? It's just what I said, you can kind of, but it's something that is not actually, recognized and acknowledged in textbooks, and it's not something that, one knew, I think, systematically how to think about a few years ago. But once you kind of think about it, it's, the whole thing is pretty straightforward, okay? But what it does give you is it gives you some kind of a completely new way of thinking about non-equilibrium quantum field theory, where correlations have this kind of a Russian doll-like structure, where there are finer and finer correlations which don't affect more coarse-grained correlations. Okay, and note that this is an exact statement. This is not like this is not like for people who know kinetic theory, you have some BBGKY hierarchy or something, or you have some Schwinger Dyson equations and you kind of truncate it, as an approximation. Okay, this is not an approximation. This is true non-perturbatively. It's an exact statement. This truncation and this hierarchy and so on. Okay, just because of the way the whole thing is defined. Okay, this is an exact statement. Okay, and the finer and finer correlations, if you really need to detect them, you need to detect them using correlation functions involving higher and higher point functions with more and more time ordering violations. Okay, there are more additional constraints which appear in thermal case, like the OTO log of KMS relations and so on, which kind of we worked out, in these papers. But let for the want of time, let me kind of skip that, like if you want, you can have a look at that, okay? But let me just say that, this kind of an exact truncation is not something, which is obvious from kinetic theory or any other standard way of thinking about non-equilibrium quantum field theory, except, this kind of argument that I just outlined, okay, where you can describe a sequence of generating functions, right? Okay. I don't know how to, for example, think about this kind of a structure of finer and finer correlations within kinetic theory. And in fact, how these OTOCs play with kinetic theory itself is a very open question. At a 4-point function level, we have some understandings, which are kind of, described in some of these papers. Okay, I realized that, yeah, so there's also a paper by, Grozdanov and Skopelity and so on and so forth, I think, which kind of went in. Yeah, so there are a bunch of papers, which kind of this thing, but I think, it's fair to say that we don't really understand how to think about, even within perturbative field theories, how do we think about the structure and how does this exact truncation work and how do we kind of make a picture of this, right? Okay. What we seem to need is some kind of an infinite sequence of distribution functions and some generalization of the notion of quasi-particles themselves, which that is some more and more finer kind of quasi-particles which transport finer and finer correlations, whatever that means. Okay, so it's kind of, I'm trying to describe, the kind of crude understanding that comes from various existing calculations by various people in the literature. Okay, and the question is that, okay, so this is the thing. So these are kind of very mathematically well-defined objects, and they also contain very novel information, and they probably have experimental consequences. I'm not given various papers which kind of try to see how you can experimentally measure such correlation functions and so on and so forth. But there's doesn't seem to be an in-principle obstacle, though in practice it does seem very difficult. Okay, I think a corresponding an analogy which one should keep in mind is the notion of entanglement itself, which kind of was born, when Schrodinger talked about Schrodinger cat and von Neumann and Einstein, Podolsky, Rosen in their very famous paper talked about entanglement. But it took many decades before entanglement became a thing that is a useful way to characterize systems, quantum systems. I think these are such kind of observables, and of course entanglement again is it's not very clear how do we measure entanglement entropies and so on and so forth. Okay, though there are some experimental protocols how to measure any entropies, some kind of information measures, but irrespective of whether they can be measured or not, even if they're difficult to measure, I think, now it is kind of accepted that they are very useful theoretical quantities to characterize the systems, to characterize the complexity of the systems, and so on. Okay. So what do we know about, this OTOCs is that, we know that, somehow these OTOCs seem to be, at least OTOCs with 2 time ordering violations, which are the things which are really have been studied. They seem to be a good tools to diagnose chaos and how complex, your quantum field theory is, and how much it scrambles and so on and so forth. So there is a decent amount of literature of this kind, starting from the famous work of, Shankar and Stanford. And also, it is also kind of thought that, this can be used to kind of characterize how close a theory is to being holographic to classical gravity, because one of the things that was pointed out by Shankar Stanford and then Madras and Shankar Stanford and so on and so forth is that there are various ways of saying what they said. So the one way of saying which I like is that, so as we know, black holes Hawking radiate, and Hawking radiation is basically like black body radiation. Okay, so it's like any other black body radiation. So you can ask, what is special about black holes? So one of the things that these people pointed out is that you can kind of define some kind of an OTO analogs of Hawking radiation. These are more finer Hawking radiation, which you cannot detect, like by using standard time ordering correlations, but you will start seeing these Hawking radiation and Hawking fluctuations if you measure out of time ordered fluctuations in near a black hole. Okay, and what they argued was that those guys are kind of very characteristic of a black hole. They kind of have some very they have a maximal scrambling kind of thing. There's a way to make sense out of it, and so on and so forth. Which is also something that I won't go into. But the point is that hence in some sense the gravity. So it has always been thought of that the black holes are kind of in some sense the best thermal baths. It's not always clear what does it mean just by looking at Hawking radiation, because if you just look at Hawking radiation, it just looks like any other thermal bath, right? Okay, every thermal bath Hawking radiates like a black body, some big enough object with appropriate this thing. But the point is that if you look at this OTO versions of Hawking radiation, those are kind of very special to black holes, and in that you can actually try to make precise what does it mean to say that the black holes are really the best thermal baths that are available. Okay, so this is a kind of a broad overview of various ideas that that have come about. Okay, but what I think should be clear in in what I'm saying is that is that what we have done is kind of barely scratch the surface of these things. So what we have done is that we have said that there's a structure of hierarchy and so on and so forth, but we do not really understand how do we kind of make sense out of this hierarchy. And this is a hierarchy which you really realize only when you start thinking about it in terms of Schwinger Keldysh Path integrals itself. And at least I do not know of a very natural way to derive this hierarchy or any of this stuff in a very kinetic theory way of doing it. There might be some way of doing it, but at least nobody knows how to kind of derive this kind of an exact hierarchy which is present in any non-equilibrium quantum field theory. But out of time ordered correlations are hence one kind of objects that kind of seem to have a very rich and they kind of sketch a very new picture of what we mean by non-equilibrium quantum field theory than what we are aware of. So since I'm kind of just giving some broad overview and I want to talk about other subjects, so let me move on. But before that, are there any questions about just this set of ideas that I'm outlined? So I'm kind of being somewhat sketchy, but without going to technical detail, because I think it's important to kind of understand the broader contours of where we are getting at. Then the details of the computation, which you can find in these references. Yeah. But are there any questions, comments before I kind of move on to a slightly related subject of how to think about open effective field theories in a non-equilibrium context? Okay. So the second theme I want to talk about are open effective field theories. Okay. So the question is that so what are open effective field theories? So here open is the adjective same as in open quantum systems. So basically what one is talking about is some kind of a quantum field theory where the environmental parts are traced out. So you think of a quantum field theory and there's an environment which is also a quantum field theory. Which you kind of trace out the environment, and then you ask whether you can write down some effective field theory for just some system degrees of freedom without the environmental degrees of freedom. So the environment could be light but fast degrees of freedom. One very canonical textbook example of an open system is just a Brownian particle, where you have like a ball or something, which kind of or a pollen. Which kind of moves through water. So it moves slowly compared to the molecular scales where the molecular motion is very fast. So you can integrate out the molecular motion to write down some effective theory, effective stochastic theory, a Langevin theory for this Brownian particle, okay? Which has dissipation, so which has them damping and fluctuation, which are the characteristics of open quantum field theory. So they're not non-dissipative standard quantum field theories, but they're kind of quantum field theories with added dissipation and fluctuations, okay? like hydrodynamics, for example. Hydrodynamics is a field theory, okay, but it is not a field theory in the standard quantum field theory because it has dissipation, it produces entropy, and so on and so forth, okay. So there are many ways of motivating why we should be studying open quantum field theories. One very fundamental question is about how to understand decoherence and dissipation in quantum field theory. For example, like we often say that, like let's say in high occupancy number, like you get a classical field theory, right? Like a QCD becomes a classical Young-Mills theory. But if you want to really characterize it, if you want to characterize how much it deviates from the classical field theory, what are the fluctuations, and so on and so forth, and how you approach it, this classical field theory, and how you kind of go out of it, okay, and so on and so forth. Like what you need is some kind of a field theory where, like these modes, which are kind of classical and so on, they become classical because, because of very high number of degrees of freedom, which you kind of integrate out to kind of give a classical description, right? Okay. And the point here is that, and it can also be because it is in contact with something can become classical also because it is in contact with some big apparatus or some bigger system. And these kind of things are very well known in open quantum systems and are very well studied, especially experimentally nowadays, okay, in quantum optics and, like in molecular physics and so on and so forth, atomic and molecular physics. These are very interesting ideas that are coming up, and one way to understand and motivate open quantum field theories is to say that, like what are the analogs of that in a relativistic or non-relativistic, for that matter, quantum field theory. Okay. So another particular application for open quantum field theories is in cosmology, where the fields are always falling out of contact. Okay, and in some sense, like if you just wanted to describe just the visible universe, right? The universe which is in a causal contact with us inside the de Sitter horizon, then, like it's a kind of an open system where things can go in and come out. Like things can kind of go out, so they can kind of dissipate, but then, that they can tunnel back in, okay, quantum mechanically. So there's some kind of fluctuations. And the question is that, like, how do you think about them? Okay, so that's another context where, experimentally relevant context where open quantum field theory is important. From a string theory and a gravity point of view, open field theories are also important in order to understand how to think about black holes, because black holes are also objects where things go in, they dissipate, okay? But then, like there's a tunneling back, which is the Hawking radiation, okay? So which constitutes the fluctuations. And the question is that, like how do you think about Hawking radiation and things falling in, within a unified framework, okay? And that also kind of, like requires you to think about open quantum field theories, where you kind of integrate out the effects of the black hole, and you kind of try to write down some effective open quantum field theory for the fields in the black hole background. So there is also, like various reasons why we want to kind of understand this as a formal framework, where we can talk about, like renormalization, various things that we know and love, right? Open operator product expansions, fixed points. Are there fixed points, relevant operators, irrelevant operators? There's a lot of things that we understand in the standard Wilsonian paradigm, okay, of effective field theories, and one wants to understand, like whether one can do this in an open effective field theory. For example, like one can ask, something relevant to many things that you heard yesterday, which is that can you actually think of hydro as a kind of fixed point, right? A non-perturbative fixed point? Can you write down some renormalization equations? And say that, like it's an RG fixed point of some open effective field theory that you kind of approach hydro, okay, in the IR or something, okay? So can we define RG flows within the, so can you set up a formalism and so on, okay? This is also something that, like is kind of something that has happened only in the last few years. So like hydro itself is a complicated problem with velocities and temperatures and various nonlinearities and so on. So like what one can do is that one can start with some kind of a toy problem, okay? A toy effective field theory, an open effective field theory, okay? And ask whether one can study, like renormalization within this effective field theory, okay? So this is what I would call as an open 5-4 theory, okay? So this is kind of an effective Schwinger Keldysh action. So remember, in a unitary quantum field theory, I said that there is an S of phi r minus S of phi l, giving you forward unitary evolution for Ket and the backward unitary evolution for the bra. Okay, but in general, open quantum field theory has also things which mix this phi r and phi l. This is the basic understanding that goes back to Feynman and Vernon in 1960s, who argued that like when you integrate out an environment, you generate like phi r phi l mixing terms. Okay. And that's what makes it non-unitary theory. So then you can just write down all possible terms, like let's say with phi going to minus phi symmetry. So you can have a del phi square, phi r to the power 4, phi cube phi l, and so on and so forth, right? Okay. So these are all the terms that you can write down. Now, of course, this action cannot be like completely arbitrary. All these coefficients cannot be completely arbitrary. Because, like one thing is that the bra evolution should be kind of the conjugate of the Ket evolution, which kind of says that the couplings that Ket fields C and the bra field C are related by complex conjugation. That you can already see if you just look at the first line and the second line. So the couplings appearing in the second line are kind of complex conjugates of the coupling appearing in the first line, which are in general complex couplings, okay, because of general non-unitary theory. And apart from that, and the couplings appearing in the third line are all real. Okay, they're real couplings. Z delta, n delta square, lambda delta are all real. So this is one condition that needs to be obeyed. Further, I remember, like when I said, like in a Schwinger Keldysh path integral, if you said JR equal to JL in the underlying microscopic theory, the whole path integral collapses, right? The whole generative function collapses to unity. And that can be made sure, at the level of, at the level of this effective action by demanding that if you set phi r equal to phi l in this effective action itself should vanish. Okay. So these two are equivalent statements. It's not very obvious, but there's some set of steps which basically show that, these two are equivalent statements. Okay. And that kind of, actually imposes some relations between these couplings. Okay. For example, it says the imaginary Z should be same as Z delta. Imaginary M square should be same as M delta square. Okay. And some combination of imaginary lambda 4 and sigma 4 should be, same as lambda delta. Okay. So basically, relates the imaginary part for the first or the second, because they're complex conjugates, to the real coefficients in the third line. Okay, which mix the phi r and phi l coefficient. So that's a kind of conditions that you get. Okay, so this is with this is a more general open effective field theory, right? These are the couplings. So I'm just writing down all possible things allowed by symmetries and some general principles which follow from some general microscopic considerations. Now already you can say that this sounds a bit funny because when you write an effective field theories, you're not allowed to kind of put some random relations between the couplings, because if you put them, you're not guaranteed that when you start renormalizing them, those relations will be preserved unless those relations are protected by some symmetry or something. Okay, so one basic question about renormalization in this open effective field theories is whether this is preserved under renormalization. Okay. So you can do a one-loop computation, okay, and you can calculate beta function. So, I mean, this is some one-loop calculation in phi-4 theory, you can look at a paper and you get some beta functions. So the important thing is that, you can calculate, how does these combinations run, okay? So these conditions are what are called Lindblad conditions, okay, which I forgot to mention, okay? So how do these Lindblad conditions, which basically come from saying that of this collapse of the Schwinger Keldysh path integral, how does it behave under renormalization? So one thing you can show, okay, is that at any order in perturbation theory, I mean you can show it at this one loop, okay, but you can also give a formal argument at any order in perturbation theory that once you set these Lindblad conditions, they are preserved under renormalization group evolution. Okay, this itself is a somewhat surprising thing. Because because of what I mentioned, that which is something unusual, some specific particular property of these effective field theories. So there's a formal argument, okay, which at least tells you that at any order in perturbation theory, if you once you set these conditions, once you set these couplings to obey these conditions will be obeyed as you run in the renormalization. Okay, that you never generate something in the beta function or something which will kind of violate these conditions. Okay, the violations of the conditions will be proportional to these conditions. So once imposed, okay, they will be preserved. So this all seems like a good news. Okay, it's all works and so on and so forth. You know, like various things. Okay, but you know, like, but actually, you know, like if you start looking at this more carefully, so there are a lot of confusing things, right? Okay, so to just kind of illustrate one of the confusing things about this thing, you know, like consider a one loop diagram. Okay, let's say you take like a D space-time dimensional 5-4 theory, okay, or something, you know, like, and you look at, you know, like some one loop diagram of this kind, you know, like where so these thick lines denote right fields and right, you know, dashed lines denote left fields, and these are kind of propagator which convert right and the left fields, which they are there, you know, like in Schwinger Keldysh. Okay, I write on an explicit path integral that this diagram represents. But this kind of diagram automatically appears when you start doing perturbation theory, you start calculating one loop renormalization in an open non-unitary effective field theory. It doesn't occur in a closed standard effective field theory, okay? But in an open effective field theory, this kind of loops occur and they correct things in perturbation theory. Okay, so the particular integral is of this kind, you know, like since I'm kind of, I think, you know, like running slightly late on time, I will kind of, you know, like just give you state the punchline that if you kind of actually calculate this integral, which you can by using standard Schwinger Keldysh rules, which I'm not, you know, explaining this in detail. Okay, you realize that, you know, like standard power counting arguments are kind of somewhat misleading. Okay, the kind of arguments that you find in Pesquet and Schroeder or Wienberg's book on quantum field theory is kind of misleading in kind of estimating the divergence of these diagrams. Okay, in fact, if you kind of carefully calculate this diagram by putting a UV cutoff and so on and so forth, what you see is that this diagram is logarithmically divergent. Okay, in any dimension. Okay, though you would see that, you know, like no, the naive counting says that in d greater than 2, this diagram should always be convergent. Okay, it should be like a nice diagram. Okay, but that is not the case. Okay, if you really calculate this, you get a logarithmic divergence. But more surprisingly, the logarithmic divergence actually is non-local in the sense that, you know, like it is not. So remember, the standard UV divergences are usually like some polynomials in, if you're calculating in momentum space, some polynomials in external momenta times log or some power of lambda and so on and so forth, right? And then you can put some counter terms and cancel them. So this is the structure of divergence even in a non-renormalizable theory. Okay, but in this kind of an open effective field theory, what you see is that it has some very funny UV divergences, which go like some 1 by k to the power d minus 2, which cannot be cancelled by any local counter terms. Okay, so these are kind of non-local divergences. Okay, which one doesn't really know what to do with. Okay, so in some sense, you know, these open effective field theories, you know, like so this is a statement in the simple theory, but I think, you know, this is a statement even in, you know, like more complicated theories than in hydro, when you start doing loops and so on. A lot of times, you know, people calculate loops in hydrodynamic effective theories. Some of you might be familiar with, you know, like various things that are done in kinetic theory to calculate long time tails and so on. Okay, but I think, you know, like a lot of times there, you know, and usually we don't care about the UV parts because we all kind of assume that the real problems are in IR. Okay, the IR divergences are there, some long time tails, various funny things happen in IR, but the UV, you know, like is kind of boring. It's just some you know, like, so it's a kind of an implicit assumption that it's just like some standard non-renormalizable Wilsonian effective theory. But this example shows that, you know, like there are kind of dragons here. You know, like we need to be slightly careful. Okay, you cannot just, you know, import everything that you know about standard Wilsonian effective field theories and start applying to dissipative field theories like hydro and so on and so forth. And this leads to a breakdown of standard Wilsonian paradigm, and you can kind of trace this breakdown to kind of the breakdown of operator product expansions within, you know, like non-time ordered products and so on. But these are all various details. But the main thing that I wanted you to take home is that if you really wanted to think of hydro as a fixed point, okay, of some RG evolution, okay, you need to define what do you mean by RG evolution, okay. You need to define what are counter terms, what are beta functions, and all the standard stuff for open effective field theories. And explicit calculations seem to see that it's not very easy. In some sense, our understanding of open effective field theories is like Schwinger, Tomonaga, Feynman, quantum field theory. It's like pre-World War. There are all the divergences, and nobody knew what to do with them in a quantum field theory. Similarly, there are all these divergences, UV divergences in effective field theory. We do not really know. They should be resummed. Are they some, secretly some IR divergences? It doesn't look like them for various reasons. You can analyze this simple example and in very much gory detail and kind of make sure that they're in fact coming from UV parts of the integral, okay? But there are some various kind of, subtleties here, which again need to be understood, okay? So again, I'm not kind of giving you definitive answers, but I'm kind of giving you some general principles and some general ideas, okay? So this is as far as I wanted to say about the second theme, okay? So Sayantan, I have about 10 minutes, or what is the?
We usually keep the last 10 minutes for questions, but you can take a few more minutes.
Okay, so I'll try to say, I just have some 2-3 more slides. Okay, I'll just.
Yeah, sure. Okay.
Okay, because I kind of thought that we run out of time. But are there any questions or comments regarding this thing? Or maybe we can kind of address any questions after the talk. Let me just say another recent development, which is about how do you do Schwinger Keldysh in holography and in black holes and so on and so forth. Okay, yeah. So for the want of time, let me just just summarize these 2 slides which I just get. So basically, the point is that what you have to do is that you have to double the black hole, right? You need to have a bra copy of the black hole and a Kate copy of the black hole, and you need to somehow stitch together these 2 black hole geometries, and kind of understand how these geometries evolve. Okay, this is not easy, and nobody really knows how to do it at this point. Okay, but this is roughly what you want to do. And that this is roughly what you want to do was pointed out by Keldysh and Wandys about 10 years ago in these papers, okay? But we do not even have some working definition of how to do it, how to even stitch together horizons, okay? And a lot of recent progress has relied upon a conjecture on how to do it, okay? So in principle, what we would want is kind of an in-principle derivation starting from, the basic equations, looking at the gravitational solutions, of the double kind, and kind of saying that which saddle point dominates, and say that, okay, so that is the geometry we should work with, okay? That nobody has done. Nobody has actually understood how to think about Einstein equations and the Schwinger Keldysh doubled solutions of Einstein equations and so on, okay? So that's still unknown territory. But what these set of people, Glorioso, Crossley, Liu, Glorioso, Liu, what they did was that, they gave a conjecture. Okay, they said, they did not say how to actually solve these things, but they just said, whatever it is, let's just assume that the endpoint of whatever that analysis is a geometry which we give. Okay, that this will be the geometry. Okay, then you can kind of do some consistency checks and see whether it gives you standard Schwinger Keldysh kind of expectations. For example, you can show that this conjecture can be used to kind of reproduce endpoint KMS relations, which is a very non-trivial check of this whole conjecture. Okay, when you kind of quantize, let's say, scalar field on this background or some string on this background, this is what we showed last year. Okay, and the point is that what this conjecture allows you to do is to study, interacting Hawking physics, okay? Interacting Hawking physics, especially, where you have things like, let's say, K Hawking fluctuations, which are coming out of the black hole, and let's say some n minus k modes which are falling in, which kind of interact by an endpoint vertex, right? So this kind of thing can be exactly calculated. In fact, like we calculated this in this paper that is in the reference at the end of the slide. Okay, this year. Okay, and we can actually like precisely calculate these things. So this is actually a very new thing which could not have been calculated before, either in perturbative field theories or in gravity or in non-equilibrium, anything, right? Like, because even in a kinetic theory, okay, even if you work in a kinetic theory approximation, okay, to kind of keep track of all fluctuations which appear in an endpoint function, to write down Schwinger Keldysh equation for some general endpoint function and kind of, solve it in kinetic theory is not, like an easy thing, right? Like to kind of capture all the fluctuations, which capture all the KMS relations, equilibration, everything. Is not like within the current abilities of anybody I know of. Okay, so it's a very very challenging thing, but holography allows us to do that, and this conjecture, if we take that to be true, okay, again it's not a derivation, but it's a conjecture, but but it passes some non-trivial checks. So you can kind of use this conjecture to calculate these kind of non-trivial things, like of what happens in endpoint function fluctuations, which is already a very nice thing when it comes to open quantum field theory and so on. So there are many generalizations possible. When we not actually talk about open 5.4, we are trying to generalize it to fluctuating hydrodynamics, okay, which is a more complicated problem, which goes back to the point of how do we think about Einstein equations in this double background and solutions of Einstein equations. But the point is that with various people, hopefully we will soon report on these like in a matter of months. Okay, so let me just since I've run out of time, let me just conclude. Okay, with a summary. So what I've talked about in the past 1 hour is about like 3 new developments in non-equilibrium quantum field theory, about out of time ordered correlations, about like new kind of insights in thinking about open effective field theories and renormalization of open effective field theories, fixed points in these things, and so on and so forth. About how do we start doing Schwinger Keldysh in holography, and how do we kind of start thinking about interacting Hawking systems, which kind of take into account non-equilibrium fluctuations in holographic systems. Okay, and this is something new and interesting, where you can think about Hawking radiation scattering and so on and so forth, and kind of you can do things which you could not even imagine a few years ago. And there are various kind of intersections that you can think about, and there are many unanswered questions and challenges. But let me just stop here, and I'll thank again the organizers for giving me the opportunity, and thank you for the patience. Okay, yeah. So thanks.
Thanks, Loga, for sharing your brilliant insights and also the exciting new results that come from your group always. So we have a lot of questions here. So Ayan, please, if you want to ask the question directly.
So Loga, actually the question was about on this slide, the CGL condition that you talked about on the horizon.
Yeah, yeah.
Right. That you have to impose to get this KMS relations. So yes. The question is it generalizable in an out of equilibrium setting?
No, not till now. Though like the fluctuating the work that we are doing now, which we are kind of finishing up to some extent, does allow you to deform this conjecture. Okay, let's say in linearized gravity, you can kind of add some gravitons, right? Slightly, in the fluid gravity kind of geometries, right? You can deviate from this exact equilibrium.
I mean, adiabatically evolving horizon, something like that? Or?
No. General deviations from equilibrium.
But hydrodynamic.
But hydrodynamic, not far away from equilibrium. Though you can ask questions about far away from equilibrium. See, the point is that this is a conjecture, right? They did not give a derivation or anything. They just...
Yeah, in this case, actually, Paul has a question which I'm asking on behalf of him also. So which horizon will it be? Is it the event horizon or the apparent horizon or some trap surface? What exactly?
Right.
Horizon?
So the way these things work is that it doesn't matter. Okay. It's a bit like, in Schwinger Keldysh, it doesn't matter where you turn in future, because the additional future evolutions kind of cancel out. Okay. So in the geometries, you can kind of turn, but you have to turn where, I mean, unfortunately, I do not have a lot of details, but what you get is some kind of a branch cut, which kind of goes because of the redshift factor. Okay. So at least in this fluctuating, like linear deviations from equilibrium, you can kind of just go and turn in the 0th order horizon. Okay. But the point is that, I mean, it can kind of go back and forth slightly. It doesn't matter so much. Okay. In fact, there's a standard result that 10 years ago, when we were thinking about fluid gravity, we proved that in this kind of slight hydrodynamic deviations away from equilibrium, you can actually think of a derivative expansion for the horizon. Okay. So these various difference between outermost marginal trap surfaces and so on and so forth, they all kind of, and the hydrodynamic regime are kind of same. They don't make so much difference. You can, of course, ask questions about very non-equilibrium situation. Let's say some Baidya geometry. Okay, what happens there? And how do we think about this conjecture there? And that's really what we want, right? If we want some things like things colliding and forming, quark-gluon plasma, and we want to dualize it. We would like to kind of, do that in Schwinger Keldysh in gravity. We do not know how to do that at this point. Okay, because there's not a derivation, it's a conjecture, and we don't really understand dynamical geometries very much. But this is still, early parts of, early stages. So hopefully, we will slowly understand hydrodynamic deviations and go from there. Yeah.
Okay, thanks.
Paul, do you still have a question, or it was addressed in Ayan's question?
No, basically, Ayan asked my question. Thank you.
Okay, thanks. The next question is by Zoran. Please go ahead.
Yeah, so well, I can read it out. So I have a question with regards to the second part. So I found it very interesting that when you consider the renormalization of these local operators you introduced, you found essentially non-local divergence structures. So what I'm wondering whether this is somehow pointing towards an understanding that when we think of effective actions to describe real-time dynamics, whether these should generally contain non-local interaction terms, for instance.
Maybe, but then like a lot of us think that you should get hydrodynamics at the end of it, right? I mean, which does seem local in some sense, right? I mean, maybe there's a way of writing it in a local way. That's what my hope is. I don't have a clear answer. Okay, so this is more, but this is a pretty clean calculation. I mean. What you're saying is a possible resolution, but it would be very unsatisfactory if that was the answer, because it doesn't kind of gel in with our, gut intuition, if you wish, right? I mean, that at least in some.
Yeah, sure. I mean, you would like to recover the hydro fixed point. I mean, this I understand.
Yeah. So there's something funny going on. Okay, which is what I find interesting. Okay, so I don't have a categorical answer. But hopefully it's not what you're saying. Hopefully, it's something, yeah.
I have a nice question here.
Yeah.
So when we talk about hydro mode, so we talk about some like energy momentum tensor, something which is nearly conserved, and we look at the long wavelength modes. So when you talk about hydro fixed point of quantum field theories, what do you mean by that? So.
Yeah, so the point is that, somehow, there is some kind of an effective action with some couplings involving hydrodynamic fields. Okay. So which, there have been a lot of proposals, including by me and my collaborators, on how this effective action might look like, which I did not talk about, with some couplings and which kind of run to some fixed points or something, right? The most naive thing is that it's like any other effective field theory. Like, how do you think about chiral effective field theory as coming from QCD, right? Okay, you kind of think of, you know, like coefficients in that effective field theory, you know, like, and there kind of some kind of Wilson coefficients, which can be you know, like computed from the microscopic theory. They themselves run and so on, okay, or any other effective field theory we are familiar with in particle physics, right? You know, like QED or, you know, soft collinear effective field. I mean, various effective field theories we know, where, you know, like we kind of have this picture of some effective field theory with some effective couplings, which can be computed from an underlying theory, and which is kind of universal, but there's some running which is captured by the effective field theory and so on. Yeah.
So universal meaning any 2-point function or
universal in the sense of the kind of thing that we heard yesterday, that there's some attractor, right? You know, like like we have universal critical points, right, in equilibrium, right? You know, like many different spin models run to the Ising fixed point, things like that.
Yeah,
okay, that kind of universality. I mean, this would be the dream, but the point I'm making is that, you know, like we need to kind of it's not as simple as just, you know, like importing everything that we know and just applying. Okay, there are new things happening here, and we need we need to understand. But hopefully not too much.
Another nice question. Yeah, yeah, go ahead, please. Yeah.
Sorry, I just wanted to briefly follow up. So I mean, in the particular example you studied, though, right? I mean, you don't have energy momentum conservation, right? So you wouldn't actually, in that, I mean, for that particular case, you wouldn't actually expect it to find any kind of hydrodynamic behavior in
right. Right. You don't expect to find any
scale limit, right? And so, I mean, so this loosely reminds me a little bit of this discussion of where this is studied in the context of dynamic critical phenomena, where sometimes then you have these peculiar poles showing up in correlation functions, and you kind of manage to patch them up by introducing coupling to some additional conserved density, which is relevant on the long scale. So maybe one has to somehow think in that direction, that essentially you have to then just keep propagating more fields in your RG flow for the conserved quantities. Right?
Yeah, presumably, presumably there should be some resolution. Maybe there's a new IR degree of freedom. You know, that, I mean, that's kind of one natural resolution, right? Whenever we get like some non-locality, it probably tells us that there's a new. But the point is that there's a non-locality in UV, which is really, you know, what disturbs the hell out of me.
Okay.
So new IR divergences is not new. Okay, like we kind of know this, right? You know, like especially in non-equilibrium field theory, in thermal field theory, you get all sorts of IR divergences, and whenever we get IR divergences, we say, oh, it just tells us that there are new degrees of freedom, there are new kind of, we should resum, or we should recast it into something else and understand and so on. And so that's all kind of, you know, like within the standard paradigm, right? You know, Wilsonian paradigm. Having IR divergences, which are new. Even poles, which are new, right? New poles, which kind of tell you that there are new IR degrees of freedom and so on.
Yeah, exactly.
But having non-local divergence in UV, which cannot be cancelled by counter terms, is a bit funny. There's obviously something wrong that is going on, okay? Because it kind of violates our naive intuitions, or maybe, yeah, but it's not clear what. Yeah, so I don't have a. Yeah, it's not clear to me. For example, adding new IR degree of freedom, let's say new conserved currents or something. How will this solve?
Yeah, no, it doesn't seem that this will fix this issue.
Solve the UV problem. But you're right that, you know, like this is very similar to the dynamical critical points, like this Hohenberg-Halperin classification. If some of you know it, yeah, there are more coupling theories. I mean, there's a set of non-equilibrium statistical mechanical ideas that this makes contact with, and it kind of, you know, like is within that ambit of that kind of things. Yeah.
I had a very nice question. So in QCD, if it's possible to have a separation of scales, like the magnetic scale is far separated from the electric scale, then can we study the physics of the magnetic scale using this open quantum field theory setup?
Presumably, though nobody has really done it, right? I mean, I think, yeah. So of course, you know, like
Sometimes those are non-perturbative also. So it's like
Right.
separating the more perturbative piece from the non.
Yeah.
For that, what needs to be developed? Like, is there lack of systematic framework or?
Yeah, offhand, I don't know, but I think, like, but at least we understand at a plasma physics level, kinetic theory level, some of this, right?
Okay.
One can try to recast it in terms of open effective field theories. Even that is not completely clear. Like, how do you think of even kinetic theory as a fixed point or something? I mean, once you start getting into this business, there are many questions which are not really, one doesn't know the answers to. So I don't know. But it's something that we should look at. Right? There are various kind of examples of this type, where there is separation of scales, and we would expect some effective dissipated theories. And how do we think about this effective dissipated theories?
I see another question in the chat box by Sumit Rana. How black hole is considered as an equivalent to thermal bath soaps?
See, the point is that black hole, so this goes back to this original idea by Hawking that that black hole basically behaves like a black body with a particular temperature, which is described by things. Okay, so that's one kind of answer to the question. A more precise answer to the question is that black hole is something where things can fall into, right? It's kind of, so in some sense it's like a dissipative medium. It's not very different from, let's say, putting a ball in a pendulum in air or something, where the energy can be lost into the medium, right? Okay. Similarly, the energy can be lost into the black hole. Okay. And so that kind of takes care of the damping part of the bath, right? So that baths do. Big systems kind of damp small systems. Okay. But there's another thing that baths do, which also they give fluctuations, right? They give like thermal fluctuations and so on. They're related by fluctuation dissipation theorems, and the fluctuations are captured by this Hawking physics. And what Hawking showed that there's a fluctuation dissipation kind of relation where apart from things that fall in, there are also fluctuations which kind of throw out radiation, Hawking radiation, and so in a very real sense, it behaves like a thermal bath. Yeah. I don't know whether that was a sufficient answer, but it basically goes back to this Hawking's idea that that black hole is really a black body. Was that a sufficient answer? Yeah. And it obeys thermodynamics, and there are various levels that one can say in general relativity why black hole is like a bath.
Okay, so at present I don't see further questions, but I think you can always type in questions or send an email to Loga with any further questions you have. And thanks again, Loga, for this exciting new talk and sharing your insights on this very exciting and new subject.
Yeah.
And I hand over to Ayan then to
thanks everybody.
take charge of the rest of the session.
Keep safe.